Okay, so in the last lecture, last Monday's lecture, we finished talking about chapter 6, right? In chapter 6, we're focusing on the inviscid and incompressible flows, okay, dynamics, fluid dynamics, right? And the governing equation for it is Euler equation, and a specific form, for the Euler equation is that we will have the Bernoulli equation, okay, if you follow the incompressible inviscid flow along the streamlines, okay. And in the meanwhile, we also prove that if you follow the along the streamline, okay, the Bernoulli equation can be also derived from the energy equation, okay. And also that be realized that for the Bernoulli equation, right, anytime you want to use it, you must make sure that those 4 restrictions is there, okay. It's inviscid, incompressible, steady, and follow the streamline. This is the first kind of situation, okay, where you can use the Bernoulli equation. And at the end of the chapter 6, we're also talking about the irrotational flow, okay. So if you have inviscid, incompressible, plus the irrotational flow, okay, have all these 3 conditions, and if the flow is steady, then we also know that the Bernoulli equation can be used inside the flow field for any 2 points. Okay, so if the flow is irrotational, additional to the inviscid incompressible flow, all right, so you do not need to use the Bernoulli equation along the streamline. You can use it everywhere, right? This is so for Bernoulli equation, okay, 2 situations. The first situation, inviscid incompressible, you must be there, steady must be there, okay. If the flow is rotational, then you only be able to use the Bernoulli equation along the streamline, okay. And if the flow is irrotational, in addition to those steady incompressible inviscid, if the flow is irrotational, then you can use Bernoulli equation everywhere inside the flow field, okay. This is what we learned in the chapter 6, okay. And so we finished talking about the incompressible inviscid flow, and we will also talk. So we will continue to talking about other kind of flows, okay, especially the viscous flow. That is chapter 8 and chapter 9, and we will not cover the full content for the viscous flow, okay, but we will just do a fundamental introduction on it. All right, and but before that, okay, we have a chapter to talking about the dimensional analysis and similitude. So what does this mean? The dimensional analysis is basically is try to study the problem. Okay, so that for example, if you have a fluid problem, excuse me. For example, if you have a fluid dynamics problem, okay, and it may involve many parameters there. A simple example like if you have a flow around a cylinder or around a sphere, okay, and if I want to, for example, I want to say that what the drag force will be that the sphere or that cylinder will experience. So if I do an experimental study, okay, and I want to measure that drag force, so what's the parameter, you were thinking that what will be involved, right? Like the size of that sphere or cylinder, like the viscosity of the flow, like the velocity of the flow, and and density of the flow, and those parameters, right, will be involved. Okay, and so when you do the experiment, you want to measure that drag force, right? You need to create a table, okay, for those 4 parameters that I just mentioned. The diameter, the velocity, the density, the viscosity. You may need to, for each parameter, you want to, make it, make the value of this parameter, to change from a range of the values, from some small value to some large value. Okay, so you have 4 parameters. So, if you want to 10 points, okay, for the velocity, 10 pounds for the viscosity, 10 pounds for the diameter, 10 pounds for the density. So that will be 10 to the power 4, right? So you actually will have 1,000 pounds you can measure. And then after you get the result, you can put the things into the table or put the things into a chart. Okay, but the problem here you already see, right? It's like I need to measure like 1,000 points. It will be very expensive to do that in the experiments. Okay, like you need to take a lot of time. You need to use a lot, use a lot of materials and use a lot of fluids to do those kind of things. Okay, and change the things. And this dimensional analysis and similitude, it's basically in this chapter. Basically, we are talking about that. In this situation, right, we have those 4 input parameters, right? And there is a way, okay, from those 4 input parameters, we can try to see that which is important. We try to reduce, reduce the number of the, this is dimensional, this number of independent parameters for the problem. Okay, so if we reduce that this velocity, diameter, viscosity, density things, okay, into a small, maybe 1 or 2 parameters, then when you do the experiments, for example, if I can reduce this 4 parameters, okay, into 2 parameters, then I just need to measure like 10 pounds on one parameter, 10 pounds for another parameter, right? So when I do the experiments, I just need to measure like 100 points instead of that 10,000 points we mentioned earlier. So make your work much easier and much cheaper. Okay, so this is what we are going to do here. Okay, we try to see that for the fluid dynamics problem, right, with all those input parameters there. Okay, how we can reduce the number of these independent parameters so that we can find that what's the most important things. Okay, and for the problem I give you, for the example I gave you earlier, okay, for the flow over the cylinder, actually after you do this dimensional analysis, okay, you will see that actually you will only have 1 parameter is important, and that parameter is called the Reynolds number. Okay, and the definition of Reynolds number I will give you later in this chapter. Okay, so you are seeing that okay, so if you want to measure the drag for the flow over cylinder, the important thing is just 1 number, 1 value, Reynolds number. So I just need to measure like do 10, or just if I just only want to do the 10 gray pounds data points, right? I just need to do 10 experiments to measure what the drag will be. Okay, but now the problem is that how we can find, right? How we can reduce this number of parameters to a smaller number. And also the Reynolds number is called a dimensionless number. What does it mean? That means that it doesn't have any unit. Okay, so the topic of this chapter is try to find those important dimensionless parameter we can use for the fluid dynamics. Okay, some parameters maybe you already heard about them before. Okay, like the Reynolds number, like the Mach number, and so on. Okay. Okay, so let's move on. Okay, this is still on the first slide. Okay, just some basically introduction. Okay, and before we do the dimensional analysis, right? So let's review the fluid mechanics equation we have. Okay, and I give you an example here. Let's focusing on the incompressible 2-dimensional viscous flow. Okay, Newtonian fluid. Okay, so we will have 2-dimensional continuity equation. So this is mass conservation. Okay, because it's incompressible, so it's in this form. And also we have the 2 momentum equation. One is in the x direction and one is in the y direction. We assume that the gravity force is only on the y direction, so that you have this additional body force on this y direction momentum equation. Okay, mu is viscosity. Okay, so this is viscous force, and this is the convection term for the momentum. Okay, so this is how the momentum is convective by the flow motion, and this is the pressure force on the x and y direction. Okay, and the first thing is that we want to do, so this kind of equation, they are dimension, we call them dimensional equation. Why? Because that for the parameters, right, for the dependent parameters, right, like the u, like the v, like the p, for the independent parameters like the x, y, and the constant rho, constant g, they are all dimensional. When I see the dimensional, okay, it means that it has the units for it. Okay, so we can do some special mass conversion of this equation. Okay, what we did, we try to convert this dimensional equation to non-dimensional form. How we do that? Okay, so we need to define several non-dimensional parameters. Okay, for example, for the x and the y, all right, we know that their unit is length. Okay, so if we can define a new parameter called x star and y star, okay, and then it will be equal to the original x and y divided by a reference length L. This L is a constant, okay, it's called the characteristic length or reference length. Okay, you can choose that this value based on the problem. Different kind of problem, you can choose a different this reference length. Okay, and so after you do this definition, right, x over L, you will see that this x star and y star, they are dimensional, they are dimensionless. There's no unit for it because x and y already has the length unit, and you divide it by L another length unit, so your unit is cancelled. So x star and y star, no unit. Okay, we call it a dimensionless parameter. And similarly, okay, for the u and v velocity, we can also, divide the original uv value to a reference speed, v infinity. Infinity usually here, we refer to the free stream velocity. Okay, and so we define this u star and v star here. Okay, and so similar to the x and y, x star and y star, right? So you also do not have any unit for the u star and v star. Okay, and the last thing is pressure. Okay, we know that pressure is kind of tensor, right? It's kind of not tensor, sorry, it's kind of stress. Okay, so we can divide it the pressure with this rho times v infinity square. You will see that this rho times v infinity square, you also get the unit of the same unit of the tensor, not the same unit of the stress. Okay, so this pressure is a Newton per meter square, right? Pascal. And this rho v infinity square, you can also see, knowing that the value is the same kind of unit of the Newton per meter square. So after you divide p over this rho v infinity square, you get and the dimensionless parameter for p. We call it p star. Okay. So after you define all these non-dimensional quantities, okay, x star, y star, u star, v star, and p star, then you can try to bring this equation, try to substitute, the original equation. You replace the u here with u star, because we know that u will be u star times v infinity, right? So you just substitute this u with u star times v infinity. Similar for the v, you substitute for v with v star times v infinity. And x, you can replace it with x star times L, right? And y, you replace the y star times L. You substitute into it. So for this continuity equation, what do you get? You will get that v infinity times u star partial over partial x star times L plus partial of v infinity of v star partial y star times L equal to 0. Right? I just replace uv xy with this u star x star v star y star. And because this v infinity and this L, they are constant, they are reference value. So you can take them out from these derivative operators. You take this v infinity L out, and then it will cancel on the both sides for this v infinity L. And what your result will get? You get simply this term. Partial u star, partial x star plus partial v star, partial y star equal to 0. Okay, you see that this this is called the non-dimensional form of the continuity equation. Why? Because that the parameter here, right, u star, v star, x star, y star, they are all dimensionless parameter. Okay, and you can see that in these cases, actually they have the same form, right? You know, this equation here and this equation, actually they have the same form. Just the only difference is that we change the dimensional parameters to non-dimensional parameters. Okay, and so this is how we derive the non-dimensional form of the continuity equation. And you can do the similar thing for the momentum equation. Okay, replace the u with u star, x with x star, p with p star, you know, y with y star, and similar for this one. Okay, and you know, remember that when you, for example, okay, for this term, for this convective term in the momentum equation, you can replace this with the dimensional ds parameter by this way. Replace the u with u star times v infinity, u star times v infinity, x with x star times l. So you get this one. And then if you have the second derivative, you can also do the similar things. Okay, and you get this one. After you substitute all these results into the momentum equation, okay, so you will make your x direction momentum equation into this form, and the y direction momentum equation in this form. Okay, for the momentum equation on the both sides, you try to divide this constant term. Rho is constant because that for this problem we assume incompressible. Okay, so you divide this term on the both sides, and your momentum equation will become what? So your momentum equation will become this form for the x direction momentum and the y direction momentum. And this is the continuity equation, right? We already shown you earlier. So this is called the non-dimensionalized governing equation, non-dimensional governing equation. Okay, and so what's the advantage we do that, right? You may asking that why we need to do this, right? So you can see the reason from this momentum equation here, because that for continuity equation is very simple, because that after you change it from the dimensional to non-dimensional, actually it's the same form. Okay, but for the momentum equation, okay, if you looking this x direction momentum equation, okay, this is same as before, this is same as before, this is same as before. Okay, what we have before is this form, same here, same here, same here. But when you take a look at this viscosity term, you will see that the viscosity term actually this parameter is changing from mu to this value. And this coefficient, right, mu over rho v infinity L over L, this coefficient actually is also dimensional. They are dimensionless. There's no dimensional, there's no unit for this for this overall terms, for these terms, because that all the other terms is dimensionless, right? So this term has also to be dimensionless. Okay, and this is the term actually. This is the reciprocal of the dimensionless parameter Reynolds number I mentioned earlier. Okay, usually the Reynolds number, okay, defined as rho times v infinity times L over mu. Okay, and it's a dimensionless parameter. Okay, when we say dimensionless, it means that there is no unit for this Reynolds number. Okay, so in another word, so if you define Reynolds number, okay, if you define this dimensionless parameter Reynolds number, we denote it as Re. Okay, and so you can see that your x direction momentum equation, actually this coefficient can be just 1 over Reynolds number, right? So from here you will see that after you do this non-dimensionalization, you can reduce, okay, your equation to including some important dimensionless parameter for some terms, and from this dimensionless parameter, you can determine whether or not this term is important or not. Okay, so for example, okay, so this is the dimensional form, right, for this equation, x direction momentum equation, right? So we know the meaning for each term, right? We know that this is a convection term for the momentum, how the momentum is moving due to the flow motion. So this is the pressure work, and this is a viscous work. Okay, and sometimes you want to, when you analyze the problem, right? Sometimes you want to see that whether or not that this viscous term, this viscous force is significant or not, right? So for example, for some flow, right? If for some problem, if I want to assume the flow is inviscid, can I do that or not? If I want to assume the flow is inviscid, it will determine that whether or not this term is larger or not, larger or smaller compared to the other two, right? So if this term is much larger compared to this one or this one, you cannot neglect this term. And if this term is smaller compared to these two, you can neglect it, right? But how you can know that whether or not they are larger or smaller? You won't be able to see that very explicitly from this dimensional form. Why? Because that this is dimensional, they have their own unit, and they have their own unit. You cannot just determine that whether or not this term is bigger or smaller simply from this mu parameter. Even this mu is small, but maybe after this mu times this u partial square u partial x square, maybe the velocity gradient is large. Okay, and so that this term, so overall this viscous term is still large. So you won't able to know that whether or not this viscous term is significant, can be neglected or not. Okay, determine only if you only know the mu. But here, if you look in the non-dimensional form, okay, so this has no unit, right? So this is assume that u star v star has the same, this is like 1, this is like 1, this is like 1, this is like 1, right? There's no unit. They are the same one here, order of 1. Okay, 1 here, 1 here. So only this term will tell you that whether or not this is important or not. Okay, because this is the one of Reynolds number, right? If this mu of rho v infinity of L. All this is dimensionless, right? And so when you do the dimensionless, you know that this term, they have to be same order. And so if this your Reynolds number is much large, in these cases, if your Reynolds number is very large, so you know that this parameter will be very small, right? And also we know that after you do the non-dimensionalization, this one and this one and this one, these non-dimensional terms, they should have the same order after you do the non-dimensionalization, because you all dimensional, not do a non-dimensionalize for these parameters based on the reference value. Okay, so all this is order 1, order 1, order 1, order 1, order 1. Okay, so if your Reynolds number is very large, so your 1 over Reynolds number will become very small. So this will become very small, so that this term can be neglected. So what's the conclusion we get here? We get here is that you can assume your flow is inviscid when Reynolds number is very large. Right? This is true for the aerodynamics problems. Like if you have the high speed air fighter is flying, okay, the Mach number is large. When I say Mach number is large, this v is very large. So when you have velocity is very large, usually your rho times v times L over mu is large, right? So when Reynolds number is large, usually for those aerodynamics problems, we usually neglect the viscous force, right? Because the Reynolds number is big. Okay, so this is the advantage that why we do the non-dimensionalization, okay, for the cause the non-dimensionalizing, okay, for this fluid equation. So this is the x direction momentum. Okay, so if you look in the y direction momentum, non-dimensionalized, actually instead of this parameter here, 1 over Reynolds number, you will have another parameters here for the gravity term, right? Because that we assume that your gravity force is only on the y direction, right? So for the y momentum equation, you have an additional term for the gravity force, and this term is also dimensionless, g times L over v infinity square. Okay, and so this term is also form another dimensionless parameter, okay, which we will introduce later. Is called the Froude number. Okay, So this will give you like this is called f false number, f square over 1. Okay. And so let's make a summarize. Okay, why we do this non-dimensionalized, why we do non-dimensionalized fluid equations. Okay, because that the first thing why we do this non-dimensionalization is that we can reduce the number of parameters. Right, before we need to, for this problem, right, we need to know the parameter involved will be rho, x, y, and mu, right? And now after we do non-dimensionalization, we will see that the problem will be reduced to two non-dimensionless parameters. One is this Reynolds number, and one is this Froude number. Okay, so we reduce the number of parameters, so we know that what is important. Okay, the important thing from this problem, okay, if we focus on the Reynolds number, the important thing is not mu itself, not the rho in itself, not v itself, not L itself. No, the important is that this product is important. If you make mu smaller and you make the v smaller at the same time, so maybe your Reynolds number doesn't change a lot too much in that cases, and your result won't change too much. Okay, so the important is this overall value rather than the individual value of each parameter inside. Okay, so this is the one advantage we get. Okay, and the second advantage we can get is that we can, based on this dimensionless parameter, we can evaluate that, for different terms, which one is significant or which one is not. Right, so like the Reynolds number example I gave you earlier, right? So if Reynolds number is very large, so this term, the viscous term, can be neglected, right? Because this is one over Reynolds number, this is. Okay, and so last thing, okay, so if you assume you have two problems, for example, okay, so if I have a small cylinder, okay, for flow over this one, so this cylinder has d1, this velocity has v1, infinity v1, okay, and has rho, okay, and it has mu1, rho1, okay, rho1 is the fluid density, and mu1 is the fluid viscosity. And if I have another problem, like the cylinder is much larger, how this sphere is much larger, okay, for the flow of this one, so this is d2 and v2, rho2 and mu2. Okay, for these two cases, and if I want to see that what the flow field looks like, and if I know that from the experiments I already measured this one, I know that what this looks already, what the flow field is for this problem already. And for this one, if I can find that the Reynolds number 1 will be equal to this rho v1 d1 over mu1. Okay, remember that I'm using the diameter d1 as a reference length here. Okay, rho 1. And for this one, similarly, you have this Reynolds number 2, rho 2 v2 d2 of mu2 Sorry. Okay, for example, in the experiment, I already measured this one. And for this one, I didn't measure it yet, but I know that accidentally, okay, the Reynolds number, this Reynolds 2 and this Reynolds number 1, they are the same. Maybe the rho v d mu, okay, maybe the individual value is not the same, but if their product is same, okay, in another word, Reynolds number, they are same. Even I didn't measure this one, I will know that I can quickly get the result of this one from this non-dimensionalized equation. Why? Because that when the Reynolds number is same, right? We know that both the problem they can be reduced to the same non-dimensionalized equation. Because this is, you see that this non-dimensionalized equation, they are only affected by this Reynolds number, for example, for this problem. If we neglect the gravity force, okay, only this one over Reynolds number is important. So in another word, okay, since we already know this result, and from this result, we can try to calculate what the U star, V star, mu P star from this problem, because it's already known. And then for this problem, we know that they will share the same this non-dimensional value as this one. So then after I get U star, V star, right? So from this one, I try to get what the U star, V star from this problem. If we already measure this one, so I can quickly calculate this U star, V star. just divided by this v velocity infinity, right? And then after I know this one, I know that because they are the same real number, so this will also be the solution of this equation, of this problem, right? And then from here, I can again to get the flow field of this one, just simply times this u star v star with this v2 here to scale it back. So it's just like a, this. So in these cases, we will see that these two problems, they are similar. They just their flow field will be similar. They just like the scaling from the same result with different parameter, right? So this is just like a, this flow field here, this result of this one, just like a scaling of this one, with by multiply by the velocity of pressure or whatever, by multiply some constant reference value, right? Because they are non-dimensional results share the same result. Okay, so yeah, in other words, okay, from this non-dimensionalization, okay, we can see that the problem with different scales but share the same dimensionless parameters, they will lead the same non-dimensional solutions. And from this non-dimensional solutions, we can easily scale it back to get the dimensional results. Okay, so this is why, what's the advantage of, why we do this non-dimensionalized for the fluid equation. Okay, and do you guys have any questions for this one so far? Any questions? No question? Okay, so this is this method is called the non-dimensional form of the governing equation. Okay. So the next method we are going to talking about is the dimensional analysis. Okay, the previous method, okay, we on the previous method, right, to when you do the non-dimensional analyzing of the governing equation, we can find that we will find those important dimensionless parameter, right? But that method can only be used if you know the governing equation, right? If you know the fluid governing equation. So this dimensional analysis is the another method that can help you to determine what the important dimensionless parameter will be. Okay, but this method is a more general method because that this method can be even used in the cases that where you do not know any physics behind. When I say any physics behind means that you can even use this dimensional analysis method when you do not know what is those governing equation will be. Okay? So now think about that. I do not know what the continuity equation. I do not know what the momentum equation. Okay, and I still want to reduce the parameter. Okay, I do not want to, when I do experiments, right? I do not want to measure all the parameters. I just want to see which one is important. Okay, and how I can find that? Okay, without the equation, you can still do that. And this method is called the dimensional analysis. Okay, so so this dimensional analysis method is better that we show it with some examples. Okay, so that follow this example, you will know that how we do that. Okay, because if we just make a pure explanation on how this what this method meaning, what's the procedure for this method, it's not very is too wordy and not very easy to explain. Okay, it's better that we just use a real example and just apply this method directly. You will see that what this method means. Okay, so here we're using an example. Okay, the same example. Okay, we will put a sphere into a uniform flow, and we want to measure its drag force for this sphere inside this flow. So the drag force we denoted as F, and the diameter of the sphere is D. Free stream velocity is V, density is rho, and viscosity is mu. Okay, so when you try to do experiments, so what are you thinking that this drag force will be? You were thinking that, okay, so this drag force will be a function of these 4 parameters, right? A function of rho, a function of mu, a function of d, a function of v. Okay, but the problem is that we do not know this function it is, right? So you may want to determine that this function from your experimental study. And how you do that, right? So you just change the, as what I introduced in the meaning, right? You choose like several points for data points for each parameters, and you measure all the value to see that how the dependency, okay, of f for each parameter, and you try to reduce your experimental data to some correlations to find what this f it is. You do the data recursion, okay, to do that if you have the experimental data, but it will be very expensive. I already mentioned, because you have 4 parameters here. Right, so it's very difficult to set up experiments with a lot of parameters you want to you involve. And so from the dimensional list, this dimensional analysis method. Okay, we try to reduce this number of independent parameters. Okay, and the result is again, okay, it will showing you that so let me give you the result first, okay, before I do this dimensional analysis. So after you do the dimensional analysis, so what you can expect? So what you expect is that you will find that right now how many parameters we have. If you include in this f, right, you will have 5 parameters. 5 parameters, right? And this 5 is 5-dimensional, okay? You have 5-dimensional parameters for this problem. And after you do this dimensional analysis, you can reduce your problem to 2 non-dimensional parameters. You will see that this f divided by rho v square of d square, okay? So this is this d square gives you the area, right? The d is, remember, this d is the diameter of the sphere, right? So d square is the area, f divided by area, so this is the stress again, stress over rho v square. So you know that this is a dimensionless parameter. And same thing here, this is the Reynolds number. Okay, so after you do the dimensional analysis, you will reduce this problem, which involve 5-dimensional parameters, okay, into 2 non-dimensional parameters. Okay, so your result, okay, if you want to, so this is the dimensionless parameter, right? This is dimensionless parameter involve this drag force F, right? So if you want to measure that the behavior of the drag force, you will see that it will be just equal to a function of Reynolds number, right? So in previous experimental setup, you need to measure 4 parameters, right? But now, after you do the dimensional analysis, you will see that instead of measure 4, I just need to measure 1. Just measure 1 parameter. That's enough to get the behavior of the drag force. Okay, so in this case, it will greatly simplify your problem, simplify your experiment setup, right? So after do the experiment, you can get a curve similar like this. Okay, you can make the x-axis as this Reynolds number, and make the y-axis as this dimensionless parameter. So you can see that what the drag force will be. You can give this the curve, and you can publish it. And later on, okay, when other people, our other engineer, they try to find the drag force for a flow over a sphere, what they can do, they just simply that for their flow condition, they calculate what the Reynolds number will be, and go to this figure you publish, find that what's the corresponding Reynolds number on the x-axis, and read from this curve to find what this dimensionless drag force will be. After you know this dimensionless drag force, you simply times this rho v square times d square. You know that what the drag will be, what the dimension of this f drag will be. Okay, so this is the result, okay, of the dimensional analysis. It serves the same purpose. Okay, it will reduce the number of the parameters involved to a fewer number of dimensionless parameters. Okay, so how we do that? So to do that using a so-called Buckingham pi theorem. Okay, so basically this theorem means that if you have a physical problem, okay, which involve this Q1 to Qn, okay, which involve n parameters, independent parameters. So this G is any arbitrary function, okay, any function. Okay, so this is the problem. And after you do the dimensional analysis, okay, you can, you can change this n dimensional parameters as a function of G, okay, to a small number of dimensionless, not independent dimensionless parameter. Let's assume that we reduce from n to n minus n. Okay, so that we can see that the problem can be really dependent on this dimensionless function, large G. This large G is a dimensionless function because that it only involve dimensionless parameter pi 1, pi 2 to pi n minus m. This pi here is a dimensionless parameter. This q is dimensional parameter. Okay, so all this pi 1, pi 2, pi n minus m, they are dimensionless because they do not have unit. And we will have n minus m of this dimensionless parameter, and we will have n dimensional parameter. So which means that we reduce the number of parameters by m. Okay, if you do not like you write in this way, you can also like rewrite the equation like move the pi 1 to the left hand side and move all the other parameters to the right hand side. So you can see write that one dimensionless parameter will be a function for all the other dimensionless parameters. You can do that. Okay, and so we mentioned that this number, this m, right, is the number of parameters you reduce. Okay, and usually this m will be equal to r. Okay, and what is r? It is r is the number of the independent fundamental dimensions. Okay, remember this word dimensions. What dimensions mean? So if you remember that what we learned before in chapter 1, when we're talking about the unit system, right? So what is the fundamental dimensions in the physics? It's 4, right? So fundamental dimensions is L length, M mass, T time, T large T temperature. Okay, so this is fundamental dimensions. Okay, so if your problem involve, for example, if this is your physical problem involve the length, involve the mass, involve the time, involve the temperature, then you can reduce your problem to this non-dimensional form. Okay, so that it will only include n minus 4 dimensionless parameters. Okay, so this m will be equal to 4 because it will involve this 1, 2, 3, 4, 4 fundamental dimensions. Okay, and if your problem doesn't involve temperature, no energy equation, okay, only the continuity momentum equation, you only have 1, 2, 3. You only involve the length, mass, and time. Then you can reduce your dimensional form parameters to n minus 3. This m will become to 3, will be equal to this r equal to 3. Okay, so but one thing you need to realize, okay, with this dimensional analysis, okay, it will only telling you that what is pi 1, pi 2, pi n minus m will be. Okay, from this dimensional analysis, okay, it only help you to find that what is this n minus m independent dimensionless parameter from this q1 to qn. It won't tell you that what this g function really it is. No, okay, you still need to determine this g function from your experimental study. Okay, so you may feel confusing, okay, for all the things I mentioned here. But if I give you an example, you will become more clear that what does this mean. Okay, so let's still using this is the problem we mentioned before for the drag on a sphere. Okay, so this is a step-by-step how we using this Buckingham pi theorem to find that what the important dimensionless parameter will be involved. Okay, so first step 1, you list all the dimensional parameters involved. Okay, so let's assume n is the number of the parameters. So for this problem, we will have 5 dimensional parameters involved, right? Remember that we mentioned that 1, 2, 3, 4, 5, right? You have 5 parameters dimensional. So this is the 5. So this force, drag force, velocity, diameter, density, viscosity. So you have 5 dimensional parameters. Okay. So this is step 1. Just list it. N equal to 5. You know that. Okay. N equal to 5. The second step. Okay. You from this physical problem, you determine that what is the fundamental dimensions. Remember dimensions, right? This is fundamental dimensions, right? So for this problem, there are nothing related to temperature, nothing related to energy, right? So we only have 3 fundamental dimensions: L, M, and T. Length, mass, and time. Okay. So for this problem, R equal to 3, right? So this is we only have we find 3 fundamental dimensions, and we call this primary dimensions. Okay, so now we R equals 3. So what does it mean? Remember, this M will be this M equal to usually is equal to R, right? So which means that you have 5 here, you have 3 here. You know this 5 minus this 3. You know that at the end you will find 2 dimensionless parameter. 5 minus 3. Okay. And step 3. So you have this 5 parameters, right? So now you need to list, okay, the dimensions of all these parameters you have. Okay. For example, okay, this is force, right? So force is Newton. So how you write Newton in this meter, meter kilogram second? How you write in Newton in that way? Because that F equal to m of a, right? So we know that this force has to be this m will give you the mass, and a is what? A is the velocity per second, right? So it's a meter per second square. So this will give you L over T square. So example, so you know that the force has this dimension: mass times length divided by square of time. So write it here. For the velocity, the second parameter for the velocity here, we know that velocity is just length over time, right? So we know that their dimension is L over T. And the diameter is simply just length. Density is mass per volume, right? So L over Q, power to the cube. And mu is viscosity. Okay, what's the unit for the mu? Newton meter per second. No, not Newton, kilogram meter per second. This is the unit. Okay, so you know that for the viscosity, okay, their dimension is mass over length over time. Okay, so this is step 3. Okay, we just list all these parameters, in terms of the primary dimensions. You list it here. And now because R equal to 3, right? So the next step, okay, is that you need to try to choose 3 parameters. Okay, you choose 3 parameters. Okay, so you try to choose 3. We call these parameters repeated parameters. Okay. Why you choose 3? Because that we know R equal to 3. Okay. So you need to, the next step, you need to choose 3 repeated parameters. And why? Because it's repeated. We will explain this in the next step. And so usually, okay, we just choose length, velocity, and sorry, this is not length. This is rho. Okay, this is not R. So we choose the density, we choose the velocity, we choose the diameter as this repeated parameter. What's a repeated parameter? Repeated parameter means that this parameter, these 3 parameters will be shown in all dimensionless parameter. Remember that from this Buckingham-Pass theorem, right? For this problem, we will have 5 minus 3. So in the end, we will have 2 dimensionless parameter as a result. So we choose these 3 repeated parameter, which means that all these 3 parameters will be shown in that 2 dimensionless parameter. Okay, so why we choose rho VD? It's just It doesn't matter. Okay, you can choose. We have 5 here, right? You just arbitrarily choose 3. Okay, you can choose that f of vd as 3. You can choose vd rho as 3. No matter. Okay, it doesn't matter which one you choose. But in this problem, okay, let's just simply choose rho v and d as a 3 repeated parameter. Okay, why we choose this, we will explain later. Okay, so after choose this, so you just set up a dimensional equation to compare the parameters to select in the step 4. Okay, so you choose 3 repeated parameters, right? So you have 2 left. I choose rho, I choose v, I choose d, right? So I have this false and this mu left. And this false f and this mu then will be called the primary parameters. So you will have 2 primary parameters. So this rho vd will be this 3 repeating parameters. So the remaining 2, which is f and mu, is called the 2 primary parameters. Okay, so for each primary parameter actually can be expressed by these 3. Okay, so after you do that, okay, for each parameter, okay, you try to so what I mean that this one can be a function of this, can be write by, because from the dimensional analysis, right, we know that this rho vd is already contains all the fundamental dimension. It already contains all length, mass, and time. So and this f is also from that fundamental dimensions, right? So we know that this f can be read as a function of this 3. Similarly, we know that mu can be read as a function of this 3. Okay, so in another word, we know that f is a function of, can be read as rho v d, and mu can be read a function of mu of rho v d, right? So in another word, so if I using this mu divided by this function, I can define a dimensionless parameter. If I using this f divided by this function, right? This function is only constant rho v d, right? So if I using f divided this rho v d combination, I can define the second dimensionless parameter. So we just this step 5, you just need to using this this remaining 2 primary parameter to find all the dimensional parameter. So first we're using f to find pi 1. So let's assume the first dimensional parameter called pi 1 will be equal to rho to a power a, v to a power b, d to a power c. This rho vd is this 3 repeated parameter we choose, and times this f. This f is one of the remaining primary parameter. And we know that this is dimensionless, right? There are no units for it. And this ABC is a constant we do not know yet. Okay, so then the next step is that you just substitute the fundamental dimension for the rho. We know that for the rho is their dimension is the mass per L length to the cubic length, right? You substitute this mass cubic length for the rho. For the v, we know that is L over t, right? So you substitute this L over t for the v. For the d is just L, and for the force F is ml over t squared. ml over t squared. You substitute all this fundamental dimension for all these 4 parameters into it, and then we know that the result will be pi 1 should be dimensionless, right? Dimensionless means that after you times all the m term, the resulting this exponent should be 0 because there are no unit. Similar for the L should be 0, t should be 0. So we have 3 unknowns, right? A, B, C, we do not know. We need to find this equation, find the ABC value. How we find that? So first we starting m. So we know that m will be a, right? Because it's m to the power of a. And then we have times another m should be equal to m of 0, right? So you have m a here, you have another m here. So m times m to the power a times another m will equal to m to 0. So in another word, this give you what? A plus 1 equal to 0. So you know that a equal to minus 1. And then second thing looks at L. So this is L will be minus 3a, right? Minus 3a here. And times another L to the power b. and times another L to the C, and times another L. So this giving you what? This giving you minus 3A plus B plus C plus 1 equal to 0. The last thing you're looking at is T here. So this T will be minus B, right? T of minus B, and you have T another minus 2, right? Times T of minus 2 equal to T equal to 0. Okay, so this is equal to L equal to 0. Okay, so what is telling you? This is equal to minus B minus 2 equal to 0. So now by just the equal, but just the equating the this potential terms for both M, L, and small t, you will get 3 equations for these 3 unknowns A, B, C. So we can solve that what this A, B, C means. Okay, we can find them. So you'll find that A will be equal to minus 1. Okay, B will be equal to minus 2. Okay, and then C will so C will be A is minus 1. Let me see. A is minus 1. B equal to minus 2. C will be also minus 2. You can substitute it to C. Okay, so this is 3 plus minus 2 plus minus 2 plus 1 equal to 0. Yeah, this is correct. And after you know this is 3 value, you substitute back to this pi 1 here. So you can rewrite this pi 1 will be just equal to F here, A is minus 2, so rho A is minus 1, so rho is on the bottom. B is minus 2, so V square on the bottom, and D minus 2, so D square on the bottom. So you find that the first dimensionless parameter pi 1 will be F rho V square D square. This one we find here, right? This is the first dimensionless parameter found, pi 1 F rho V square D square. And the second one, right? So remember that we find this dimensional parameter by using these 3 repeated parameter and this 1 primary parameter, right? So you can find the pi 2 using these 3 repeated parameter and this mu as a primary parameter. Okay, so you can define this pi 2 will be rho times d times ve, rho to power d times v to power e times d to power f times mu. Okay, and again, you substitute the dimensions for the rho v d mu. Okay, rho will be this one, mass or length cubic length, and v is L over t, d is the length itself, and mu is mass L over LT. You do it here, and the result should be dimensionless. And again, okay, you're just equating this exponential terms for each m, L, and t, so that make it equal to 0. On the left hand side, right hand should be 0. You can solve that what this d, e, f value will be. Again, okay, 3 equations for 3 unknowns. And after you find the d, e, f value, you will find that d will be what? D will be minus 1. E will be minus 1, and F is also minus 1. Right? You substitute this your result here. You find your pi 2 will be mu over rho d, rho vd. Excuse me. So what is this? This is 1 over Reynolds number. Okay, we just using d for the length. So this is 1 over Reynolds number. So you find the second dimensionless parameter. You find the second dimensional parameter. Okay, so now let's go back to this Buckingham-Pi theorem, right? So for a problem with for a problem for the 5 dimensional parameters. Okay, we have 5 dimensional parameters, right? F, V, D, rho, U, mu. And after we do this, dimensional analysis, we find that it can be reduced to a problem with 2 dimensionless parameter. Pi 1 is that this term, and pi 2 is the 1 over Reynolds number. So you can write this pi 1 as a function of pi 2. You can write pi 1 as a function of pi 2, right? So now we find that for this problem, okay, we can reduce the, this problem basically is to 2 dimensional parameter by using dimensional analysis. Okay, and the last step, okay, is basically just it's just verification. Okay, you can just try to make sure. Okay, just try to put all the dimension to this to the pi1, pi2 you find here. Put all the dimension for each term to make sure that this pi1, pi2 is really has no unit. Okay, so the last step is just a verification step. Okay, so this step 1 to step 6, okay, is a details procedure that how you can find the how you do the dimensional analysis. Okay, and again, okay, let me emphasize what's the purpose of the dimensional analysis. Is that give you the condition that even you do not know the governing equation. Remember this dimensional analysis, right? We do not know the governing equation. We do not know the differential equation. Okay, we just simply by analyzing the fundamental dimensions, by just simply analyzing that for each parameter, what their fundamental dimensions are, they mass, what their fundamental dimensions for the mass, for the length, for the time, right? So that we can reduce that the number of parameters to a smaller number of dimensionless parameters. Okay, we reduce the n dimensional parameter to n minus 3, because for this problem m equal to 3, right? We have 3 fundamental dimension. So 5 minus 3, right? 5 dimensional parameter to 2 non-dimensional parameter. So this is the procedure for the dimensional analysis. And so this is how we here, okay, we're using this example, right, for the flow over a sphere, right? How we calculate their drag, and using this step 1 to step 6 to showing you that how we do the dimensional analysis. And on your textbook, so this is the example 7.1. Okay, so this is actually the detailed procedure is on your textbook for this example 7.1. It's showing you that one. So this is step 1, step 2, step 3, step 4, step 5, and step 6. Okay, so this circled number here is for each step to show you that how we do the dimensional analysis. Okay, to reduce the problem to only involving 2 dimensionless parameters. So after you find this, after you do the dimensional, after you do the dimensional analysis, right? So even I do not know any governing equation for it, I will know that if I want to do experimental analysis to study this drag for the sphere inside a uniform flow, I only need to measure this Reynolds number, right? Because this is a reciprocal Reynolds number, right? So that to measure that what this dimensionless drag force as a function of Reynolds number, so that I can go back to say, okay, this chart is enough for the problem because it will only involve 1 parameter for this dimensionless drag force. So this is pi1, this is pi2, right? So any question here to show, for this dimensional analysis? Anyone? No question? Okay. So we have another example, okay, to show you that how to do this dimensional analysis. Please read it yourself. So we will go through it together. All right, so for this problem, okay, we want to measure the pressure drop delta P, okay, for the flow, for steady incompressible viscous flow, okay, inside a straight pipe, horizontally straight pipe. Horizontal simply means that we can neglect the gravity, okay. And the pipe length is L, average flow velocity is V bar, and the fluid viscosity is mu, pipe diameter is D, and fluid density is rho. And also assume that we know the average roughness of the pipe, the surface roughness of the pipe. and the roughness E, okay, has the same unit as the length. Okay, so we want to reduce this problem, right? To see that how many can we reduce this to a smaller number of dimensionless parameter, right? So first, step one, the circle one here, you list all the parameters, dimensional parameters involved. So delta P is what we want to measure, and we have rho, we have mu, we have V bar, we have the pipe length, pipe diameter, and pipe roughness. Okay, and then step two, we choose the fundamental physical dimensions, right? We again, okay, doesn't involve the temperature, so we just simply select the mass, the length, and time. Okay, we select MLT. So for this one, we know that n equal to 7, so this 3, r equal to 3. So we know that we will find that 7 minus 3, we will find 4 dimensionless parameters for the problem. Right? We need to find pi 1, pi 2, pi 3, pi 4. Okay, and step 3, you list the fundamental dimensions for each parameter. Delta P is m over LT square, and rho and mu, same as before, velocity is same as before. Pipe length, pipe diameter, pipe roughness, they are all same L. They are all dimensions of L. Okay, and then step 4, we choose the repeating parameter, right? Because this is 1, 2, 3, right? R equal to 3. So we need to choose this m equal to r equal to 3. We need to choose 3 repeating parameters. And why we call it repeating parameters? Because these 3 parameters will be shown in all pi 1, pi 2, pi 3, pi 4. So that's why we call it 3 parameters. And here we still choose rho, V, and D. Okay, so what's the other thing left? Rho, V, and D, right? So we have 4 primary parameters left: delta P, mu, L, and E, right? We have 4 primary parameters. And for each primary parameter, we can define one pi value, right? One dimensionless parameter group. So for delta P, we simply like a rho times to the power A, V to the power B, D to the power C, delta P. We define the pi 1. Okay, you substitute the dimension, fundamental dimension for each rho, V, D here, and P, delta P. And you're just equating the exponential terms, and the result will be 0 for m, 0 for l, 0 for small t, and 3 unknown 3 equations. You can find what the ABC will be. After you find this ABC value, you substitute back to this function for pi 1, so you can define the first dimensionless parameter pi 1. Will be this one. Pi 1 it will be equal to delta P over rho V square. Okay, remember that pi 1 you obtain it from this primary parameter delta P, right? So using the second primary parameter mu, okay, you use the mu here, you can find pi 2. Okay, similar idea. Okay, repeated parameter is shown here times the primary parameter, and this DEF is unknown coefficient. You find it by equating the terms, equating the dimensions, make it dimensionless for this pi 2. And after you find this unknown parameters, DEF, you substitute back to this pi 2 equation, you find the pi 2 again. So this is the 1 over Reynolds number again, okay? Rho VD or mu or rho VD. So pi 2 will find it. And again, okay, using the third primary parameter L, pipe length, you substitute L here. Again, you find what the pi 3 will be. You find pi 3 will be simply 1 L over D, right? Length over diameter. And the last one is this roughness E, right? Put the roughness E here. You can find that the last dimensionless parameter is E over D. So you find pi 1, pi 2, pi 3, pi 4. Okay, so step 6 is just that to do the verification to make sure that this pi 1, pi 2, pi 3, pi 4 is dimensionless. And finally, okay, this pi 1 is what we want to measure, right? Because we want to measure delta P. So you see that you can write this pi 1 as a function of pi 2, pi 3, pi 4. So basically, if you want to measure this pressure drop in this flow in this pipe, you will know that it's only a function of this 1 over Reynolds number. This is dimensionless pipe length, L over D, right? Dimensionless pipe length, and then dimensionless roughness, E over D. So when you try to do the measure, you just need to create a table that So a number of data points for this one, a number of data points for this one, a number of data points for this one, and then what's the measure value for delta p for this value for each point. After you get the result, you can create a chart, create a table, or you do the data recursion. You can try to reduce it to some empirical correlations, right? So this is another example that showing you how to do this dimensional analysis. Okay. So in our textbook, there is another example. So I will leave this one for you to read it yourself. Okay. But it's just same idea. Okay. That same 6 steps. Okay. First step, list all the dimensional parameters. Step 2. Okay. And try to choose the primary dimensions. Usually it's just MLT. Step 3. Okay. List all the parameters. List the dimensions for all the parameters you have. Step and so that you know that was the just list it there. And step 4, you choose the repeated parameters, right? Step 5, and after you choose the repeated parameters, and then the left will be the primary parameters. So for each primary parameter with the repeated parameters you choose, you can define one dimensionless parameter, and you by equating the exponential terms for each dimension, you find all those unknown constants. You know that what the dimensionless parameter will be. This is step 5. Step 6, then you can do a verification to make sure that this pi 1, pi 2, pi 3, pi 4 things you find, they are dimensionless, right? So this is how we do the dimensional analysis. Okay, and so this is the second method you can do the dimensional analysis. The first method I mentioned before is that you can do, if you know the equation, right? You can do you can do the non-dimensionalizing the differential equation. The second one, that even you do not know the equation, you can using this dimensional analysis, you can find that what is the important dimensionless parameter. Okay, one thing you need to, I want to emphasize again is that the dimensionless parameter, this pi 1, pi 2, pi 3, pi 4, you find it there, they will be independent to each other. They must be, okay, which means that the Reynolds number you find will be independent that the dimensionless drag force. Okay, you cannot, they are just they represent different things. Okay, and the second thing is that for the step 3, not step 3, step 4. For this step 4, right, when we choose the repeated parameters, here we choose rho VD, right? As I told you, right, you can choose other parameters. You can just choose arbitrary 3 from these 5 parameters. But here we choose rho VD. There is a reason behind this. The reason behind this is that because these 3 parameters will be shown after you choose them as the repeated parameters, right? These 3 parameters will be shown in all dimensionless parameters you find. And so it's better that you choose your repeated parameter with the values that easy to measure. Okay, here the reason we choose rho VD, because that the density, the velocity, the diameter of sphere is usually easy quantities you can measure in the experiments. It's not like the mu viscosity. Usually it's not easy to measure the viscosity in the fluid, right? So I do not choose mu. And also we didn't choose F drag force because this F is what we want to measure. This should be the output, right? So we didn't make it the repeated parameters. Okay. So although, okay, you can arbitrarily choose 3 repeated parameters here, and the reason we choose rho VD is just simply because these 3 parameters, they are easy to measure in the experiments. Okay. And for a special case, okay, and if you are n minus m equal to 1, okay, n is the number of parameters, dimensional parameters, right? M is the fundamental dimensions. Okay, so if you only have 4, for example, if you only have 4 dimensional parameters, and you have 3 dimensions, right? MLT, so 4 minus 3 equal to 1. So in the end, you only have one dimensionless parameter found. And in this special case, this dimensionless parameter had to be equal to a constant, because that from this Buckingham theorem, right? You know that it has to be right as function of the other dimensional parameter, right? So if you have only pi 1 left, so the right-hand side has to be a constant value. Okay, so there is a special case here. Keep this in mind. And here we finish talking about this dimensional analysis method. And do you guys have any questions so far? Any question? No? Okay, so so I will finish here for today's class. And homework. For the homework for the last chapter, chapter 6, that in viscous flow is already assigned on the blackboard. So please working on it, okay? And the deadline, I think I said is like 2 weeks from today, okay? And so that will be the Monday of that Halloween week, okay? So try to do it earlier. Any other question, guys? Anyone? No question? Okay, so on Friday, I will continue the topic of this dimensional analysis and similitude, okay? So next Friday, I will try to finish this chapter 7. And also that, I will also go through all the midterm 2 problems on Friday's class, okay? And so that you know that where you're correct and where you're wrong, okay? And so no problem. I will see you guys on Friday. All right.
Thank you, Professor.
Yeah, you're welcome. Bye, everyone.